For some time, we have been trying to predict the performance of LEGO locomotives based on their driven weight and motor configuration. We thought we needed the dynamometer car to verify our calculations, which may or may not be true. Either way, the theoretical results and the practical results were not agreeing, and we initially thought the problem lay with the dynamometer, hence all the tweaking and tuning seen in the last two videos. Gradually, we came to the conclusion that our math had to consider the inefficiencies within a locomotive. Our previously performed and admittedly inexact testing still showed that a poorly designed drivetrain can sap a ton of power exponentially. We had wanted to better quantify these losses, but at the time, we did not know how to get a device that could apply a continuous known load to a running source. We had actually stumbled upon the answer to this problem with the static test. It does not do a good job determining the practical performance of a locomotive, but it does apply a continuous known load to the engine. From the force on the scale, we can actually calculate the actual torque at the wheels. And if we measure the speed of the drivetrain, Philo can tell us the theoretical torque at the motor. The difference goes to drivetrain losses. With this setup, we had inadvertently built a prony brake, albeit a complicated and invariable one. A French engineer invented this device in 1821 to measure the torque produced by engines. Exactly what we want. Fundamentally, a prony brake converts torque into a linear force by gripping an axle with an arm that pushes or pulls on a scale. Tightening or loosening the grip increases or decreases the rotational load and the linear force. With this in mind, we built a dedicated LEGO prony brake. It will go through a few iterations, but the overall design will remain the same. A brake pad connected to a freely spinning arm engages a driven wheel, and the resulting moment presses the arm onto our scale. A worm gear allows us to gradually adjust the braking force, and using the data from the scale and the speed computer, we can now plot our own torque curves. To see how well it worked, we ran this bog standard L motor, took some data points, and threw them into Google Sheets, plotting speed versus torque. To go from grams on the scale to Newton centimeters, we had to convert to kilograms, add gravity, and account for the length of the arm. The data formed a line starting at about 440 RPM and ending at about 18 Newton centimeters, and an R squared of 0.99 indicated a very good fit. While the predicted 18 Newton centimeters stall torque matched Philo's exactly, the measured 440 no-load speed did not. We attributed this to motor variation. We considered voltage differences, but our attached multimeter showed between 8.8 and 8.4 volts, lower than Philo's nominal 9 volts. Still, this test gave us enough confidence in the device to do some original testing. We decided to test the efficiency of 12-tooth bevels, gears very commonly found in many of our trains, and potentially very inefficient due to their small size. We tested 1, 2, and 3 bevel gear stages and plotted the results on the same sheet. The plots got a bit messy and the correlation decreased, but the overall trend was clear. Each additional stage made the entire drivetrain about 25% less efficient. With this figure in mind, we could check if the actual output of the 2-stage BR24 matched our expectation. In an instrumented static test, the engine pulled 168 grams while the wheels spun at 200 RPM. Doing some additional math got us 2.7 Newton centimeters and 333 RPM at the motor, and this data point actually fell close to but above Philo's curve. The discrepancy could come from a variety of confounding factors, which we may investigate further in the future. First, the speed computer only has a resolution of 20 RPM, which contributes more and more error the slower a system runs. Second, the ad hoc construction of the tested gear stages might generate more friction than the more properly supported setup inside the BR24. Third, we only tested 12-tooth bevels, whereas the locomotive has a 20-tooth bevel, and larger gears are typically more efficient than smaller gears. About the design of the brake, we originally used the small pulley wheels because they had smooth rubber tires, but these tended to slip on the wheel as well as the brake, causing speed and torque fluctuations. The tires themselves would also eventually wear out. The later versions with a felt pad and an Acrobat wheel slip more smoothly and in one place, and the felt pad does not damage the harder plastic wheel. Finally, with the prony brake, we can also gather better data on motors that Philo has not tested, such as the small angular motor from Spike Essentials. Running the same test as before, we observed that this motor has a no-load speed of about 120 RPM, and we predict that it has a stall torque of about 7 Newton centimeters. In a future video, we can finally get a better picture of how the fake power functions motors perform. Also a future video, circuit cubes. On that note, this is the end of this video. Please consider subscribing if you like what we do, and have a nice day.
Now we do that.
We're only going to get one data point.
Yes.
Okay. Ready?